Okay. So today I want to finish the second part of chapter 2. There will be a lot of information that you will hear today that's encyclopedic. So if you don't understand some of the details of some of the models in the first couple of slides, it's not the end of the world. For example, we're going to do a queuing model, and I'm going to immediately give you a closed form formula for delays in queuing, but I'm not exactly sure how, if it's even correct in the textbook. So even if, you know, I'll highlight what's important, and if you don't get some of the details, that's fine. Now, what will be important to understand, and it might be difficult to digest the first time you see it, are models for risk aversion. So value at risk and conditional value at risk are things that are important that we will cover today, and you'll see also some technical details. Even if you don't get it the first time around, that's if you don't get all the details, that's fine. We will have also a numerical exercise where you'll be able to actually play with the model and get a better feel for how it behaves. Okay, that said, I decided to cover all of the remaining paragraphs of chapter 2 except for 2.8, which is an example that Matthew will cover in the training section. In paragraph 2.11, you will probably hear in the first two parts in linear programming and duality, you'll hear a lot of stuff you've heard before, and then there will be two last slides in today's lecture where we will do something that can take up 2 courses of more details, and we're actually going to spend the 2 courses, not the immediately next one, but 2 weeks after that. We're going to do specialized courses on duality and subgradient methods because they will be very useful for your for the upcoming classes. So those parts of the lectures will be inspired by Stephen Boyd's slides from Stanford. And Berger and Levaux just go through this material in a page and a half, but they use it a lot later, and we're also going to use it in algorithms that we're going to cover beyond the Berger-Levaux book, specifically Lagrange relaxation. So it's good if we get a firm understanding. So the last 2 slides of today's course, we will see more details in the upcoming lectures. Okay, and this is an example of this. Section 2.6 is an example of material that's encyclopedic in a way, so it's good to understand that these models exist, but it's not necessary to get the exact formulas. So the takeaway from section 2.6 of the book is that sometimes you might have models for which you may want to avoid writing a second stage optimization problem because it's not very practical. And the reason it might not be very practical is because in terms of the number of scenarios, it's enormous. So for example, in routing problems where you have, for example, a stochastic version of the traveling salesman person problem, that is an integer optimization problem. And then if you add uncertainty about whether a client is in a certain node or not, it becomes too large because it's combinatorial. All the scenarios of where you could go, what nodes you could visit, and whether your customer is there or not just creates too large of a second stage problem. So instead what we do is we make some simplifying assumptions and derive a closed form formula for computing the second stage cost. And an example of that is available in paragraph 2.6. So what we're trying to decide here is we've got a bunch of, it's pretty similar to the model we saw last week. So we've got a bunch of customers indexed by I, and we need to decide a location for putting some facility, and the context, the specific application is an ambulance facility, and there are certain options about where we can put this facility. The trade-off is that we have a Poisson arrival model for incoming requests for the ambulance, and what we want to do is we want to and there a certain fraction pi of the request is coming from each of these areas. So what we want to do is decide where to locate our ambulance so that as we have arrivals of requests, we're sending the ambulance to a certain customer, we're coming back, the queue builds up in the meantime, so we send the ambulance to another customer, we come back, and so on. So what we're shooting to minimize is a sum of the time customers wait in the queue plus the time it takes to go and help them out. The average of the time it takes to go and help them out is this expression here. So t of I comma x is the time it takes to go help out customer I if we've located at location x. So the average traveling time for all customers is summing up from over the weight pi. So the fraction of requests that are coming from location I is pi, and the average time is t bar of x. Now then, we also have a closed form expression for how much time you also spend waiting in the queue, and that's a function of the arrival rate lambda of the request, as well as the service time it takes for the ambulance. If you're doing queuing theory, this formula over here might look familiar in terms of waiting time. I'm not doing queuing theory, and to be entirely honest, I didn't make an attempt to find the origin of the formula. And also, this is something that Matthew pointed out. The equals 0 otherwise, the way I see it, would lead to an unstable queue. So I'm not, but this is what is in the book, so I'm not even sure if the formula is correct or if there's a typo. The bottom line is that you just get away with an approximation of what's happening in reality by having a closed form expression for the value function, and then you can minimize this v of x over your decision of where to locate. The trade-off being that if you really want to locate close to a certain customer, if their weight is higher, then it takes you longer time to go and serve these other guys. And those other guys are spending more time in the queue. That's really the gist of it. Another example that's provided in the book is one where this is the example I touched upon a bit earlier. We have a traveling salesperson problem. So what the TSP problem says is we have a network of demands, again indexed by 1 to n. And we are starting from a certain node 0, which is a depot, and we want to, this graph is complete, so all nodes are connected with each other. We have to decide what is the tour that will cover every customer exactly once at the minimum cost. This is one of the most famous problems in combinatorial optimization. In its deterministic form, you can tackle it using dynamic programming. In the stochastic version of the problem, a certain customer might not be there, so we skip them. So the setup of the two-stage optimization problem is I decide in advance, the day ahead, about the tour I'm going to make, and in the actual day, I get to travel from node to node, but if the customer is not at a certain node, I just skip that node and go to the next node. So it's not, an easy solution. You can't really eyeball it very easily. And the issue here is that describing the second stage of doing the trip, you could write it out as an integer programming problem with a ton of scenarios. So for example, if you've decided that this is the tour you want to take, first branching of the scenarios is customer at location 1 there or not? And then you have a branch of uncertainty. Second stage of branching is customer 2 there or not? And this thing will just explode after a few customers because you have an exponential increase of the branches as you're looking at more and more nodes. You really don't want to type that into an optimization problem. You don't want to write this up in AMPL because the memory will collapse if not anything else. So instead what you do is you derive a closed form solution for the delay of for the cost of the trip, because the problem has a specific structure and you can use dynamic programming to solve it. So what's the structure we're going to exploit? We are going to define a function t of k, where this function says what is the average length I expect to travel if I am at node k at the moment and I want to get back to the depot, because I have to end up back in the depot. And that really depends on when you're sitting at k, how many people that you're going to visit next you expect to be there versus how many you expect to be gone. And what the formula here is doing for computing this t of k is a dynamic programming recursion. So the rationale is the following. When I'm sitting at k, one of the following things could happen. Customers well, let's think of it the other way. What would be the cost of making this trip if the next customer and the one after that and the one after that up to k plus r are absent, and then the r plus 1 customer is there? The cost of that trip would be c of k comma k plus r plus 1, because I don't even bother visiting the guys before k plus r plus 1. I immediately jump to k plus r plus 1, so I miss that part of the cost of the trip. And then I'm left with, by definition of what t is, the rest of the trip. Well, what are the chances of that occurring? You have to have a simultaneous occurrence of the following events. K plus 1 is not there, so this is the probability of that happening. K plus 2 is not there, so you're taking the product of 1 minus p of k plus j running from k plus 1 up to k plus r, and then k plus r plus 1 has to actually be there. So you can write this recursive formula for t of k. You have the boundary conditions, so when you're sitting at node n, 1 before the end of your trip, you know that the cost is Cn0 because by definition customer n is here. So you have these boundary conditions for t of k, and you can compute back the cost of the trip without actually having to model it as a second stage or a multi-stage decision-making problem. So there are some shortcuts in specific problems for getting away with not having to compute a value function in a difficult way. Is the formula here clear? And one thing I forgot to say is, so what the formula here is doing is it's saying this is the cost weighted by its probability of occurrence of not finding anybody from k plus 1 up to k plus r, and then the summation here is saying that when I am sitting at t plus k, I have to sum this up over, so who was it that I found first? Was it this guy? Or was it that this guy was absent and then I found this guy? Or was it that these two guys were absent and I found this guy? So this partitioning of the outcomes is what the summation is doing here. It's running from r equals 0, which means you're at position k, up to r equals n minus k, which means the end of the tour. That's what the formula is doing. And like I said in the beginning of the class, it's worth sitting down and trying to understand the recursive formula here, but even if you don't get the full details at the moment, it's not a disaster. Okay, yes? How do you take advantage of this? What do you do with this, is what you're saying. So, basically what you get is, you tell me a tour, I will make this computation, and I will use the t of 0 as the cost of your choice of tour. Do we agree that computing t of 0 is very easy from this recursive formula? The alternative for computing t of 0 would have been to set up a multi-stage stochastic program in AMPL, but that would have been enormous because of the size of the scenario set. Whereas this recursive formula will give you exactly the same answer, but just using Bellman's dynamic programming principle. And then the way you use it is, so is that clear? We start from n minus 1. So computing, for example, t of n minus 1 is equal to summation from r equals 0 to n minus 1, which is basically 1, right? And then we take this product here. So r is running from 0 to 1. And then we have 1 minus p of k plus j. P of actually finding someone there. And then you see how it goes on. This is just one multiplication and two sum within a summation. So it's basically, since you're summing over two indices, it's just two multiplications and then summing up the result. That's how you get t of n minus 1. Given t of n minus 1, then you move to t n minus 2 using again this formula. And you step back until you hit t of 0. And you're done. Instead of having to solve this enormous thing in AMPL, you got t of 0 just using Bellman's principle of optimality. So when you proposed to me this specific tour, I came back to you by solving this recursive formula and told you it costs this much. You want to propose, and then you can solve this problem in principle by trying out all of the different tours, which is an enormous combination, but still this formula helps you deal with the second stage fast. Is that at all clear? Or
is it obvious that it gives the same result as the huge tree? Or?
Come again?
Is it obvious that it gives the same result?
It's if you have you encountered dynamic programming before? Okay. So the reason it does give the same, it's not obvious, and it required Bellman to figure out that it does give the same answer. And you could actually spend an entire course on dynamic programming to see why it's the case that the principle of optimality works. But we can have a tete-a-tete on the break about like a simple two-stage example where you can at least understand the intuition of why this works. Certainly not obvious, though, but extremely useful and practical. Have any of you encountered dynamic programming before? Okay. It's not, we do use it to some extent in the class, in the stochastic dual dynamic programming algorithm, Maybe I could throw in an hour on dynamic programming somewhere down the line, although it's not explicitly covered in the book. Okay. Moving on. So, well, and one last remark, I guess, since we're on the topic. The whole spirit behind the principle of optimality is that when I'm solving a multi-stage decision problem, and I'm making, and I look at suppose I knew, when I face a multi-stage, and don't even think of uncertainty now, just think of making decisions in multiple stages. For example, in the traveling salesman problem. There will be one optimal route. There will be one choice of a tour which has the slowest sum of distances, right, in the deterministic situation. What Bellman thought is, okay, I'll take that tour and I'll look at it carefully. Suppose then I go at step K of that tour. And I now ask you, find the cheapest way to go from K to the end, but ignore the rest of the nodes. Just focus on this subset of nodes. That Bellman's idea was that that part of the tour has to be, you can immediately find that part of the tour by looking at the original optimal tour. So if the original optimal tour followed this path from point K to the end, then the answer to the question, what's the fastest way from this point to the end, is this specific choice of tour. So an everyday way of saying that is, forget about the past. When you're in a certain situation, do the best you can from that point to the end of time. That's the interpretation of that. And once you understand that, then you basically create a function that says, what is the best I can do from point K to the end of time? And you just call that T of K. And then you just take advantage of the fact that you start from the end of the decision-making process. And at the end of the decision-making process, when you're left with only one or two nodes to visit, it's easy to compute what the optimal path is because it's very few decisions to make. And once you compute that function T, you don't have to recompute it. You just store it in memory and recall it when you're needing it for computations from earlier stages. That's the spirit of it, and I will move on. Okay, so probabilistic, yeah, so the content of this part is probabilistic programming. So, like I mentioned in the previous class, probabilistic constraints are just another way of expressing, basically avoiding to write too many details about the second stage of decision making. You just say that I want the first stage of my decisions to give me some guarantees in terms of the likelihood of things not becoming really bad. I want that probability to be bounded. So that way we get to just impose constraints on first stage decisions and avoid modeling all of the second stage. So probabilistic constraints are a way to simplify our model in a sense. And there are three examples in the book of how you can use this. So one was the allocation of seats problem that I discussed in the first lecture. So there what we had was we were deciding how many seats to allocate to economy class, business, and first class. And when we're making that decision, the optimal thing to do really depends on how many people show up for each of these classes. When you have a first-class customer and you're charging him $5,000 to go from New York to London, you really want to treat him nice. And you don't want to turn around to this guy and tell them that, turns out we got more people in economy than we expected, so you're also going to have to, it turns out we got more people in first class than we expected, so we're going to have to bump you back to business or economy, and this guy will be really pissed off, and then you have to send him chocolates and flowers, and it's not. I'm not kidding. We had one student of Dimitri Bertsimas, he's a professor at MIT. I don't know if you've heard of him. Very well-known professor. One of his students made a startup for very high-quality services to dirty, rich people, and these things happened, and they had to send these people gifts to make them feel, to apologize. So you maybe want to say that I want to be doing this, but you know, the guy wasn't the PR person. He finished operations research in MIT, but then he was using all the models on chance constraint programming to actually run a company out of it. And then he had to deal with this stuff too when this occurred. So one way to write that up is you want to say the chance of not being able to serve a first-class customer. So Xi is the number of customers of first class that show up that day. X1 is the number of seats I've decided to have allocated for those people. I want the probability of the number of seats being more than the number of first class customers to be at least 98%. And then also I want to avoid the same situation with the combination of first class and business, because if the sum of first class and business customers that show up is more than the number of seats that I've allocated in first class and business, then I have to bump some of the business class customers to economy. So two probabilistic constraints. So the way you get this looks like a weird constraint to have in an optimization problem, but it just boils down to a linear inequality on the decision variables. So if you know that this is normally distributed with 16 mean and a 16 variance, and the business class customers are distributed with a mean of 30 and a variance of 48, all you need to do to ensure this probabilistic constraint is you know that since Xi f minus 16 divided by the standard deviation, so the square root of the variance is 4, you know this is a standard normal Gaussian variable. So then if you know the 98% quantile of the Gaussian random variable, you just want to make sure that Xi f minus 16 over 4 is less than or equal to that quantile. And this is just a, actually this is the number of first class, so then if you want to make sure this is true, that translates into a lower bound for the number of seats you need. So all you get is one linear constraint, linear inequality for x1 and one for x1 plus x2. Okay, which is very easy to incorporate computationally to the problem. And other example, so here the derivation was direct, just by deriving the expression for the standard Gaussian distribution. Then you can have, maybe sometimes you have to play a bit to get a formula that's linear in the decision variables, and here's another example of that. So here, in this example, we have a covering problem where we're deciding, we want to, we have n locations that we want to serve, and typo. No, correct. An investment cost Cj for each of the locations. Sorry, n locations where we can actually decide to locate. Investment cost of Cj for locating in those locations, and m clients indexed by I that we want to serve. And we have only certain sites that can serve certain customers, and the condition for this to be true is that the distance of the site from the customer cannot be above a certain limit. So basically all that's saying is that our total service area is partitioned into these pieces, and you know, actually this can even go beyond. So this site can serve two different customers. And we want to minimize the sum of the investment cost so that we are able to serve all customers. And that's just a combinatorial optimization problem where for each customer we have to serve him from at least one area. We're minimizing the investment cost over all areas, and the stochastic version of the, and it's a binary decision variable. Now the stochastic version of that problem says that, well, when I'm actually asking for a service from this location, it might be the case that it's occupied and that service, this location cannot serve the customer. So if we want to impose and the probability that this location is unavailable for service is little q. If we want the chances of this occurring to be, what we want to ensure in this model is that the probability that at least one emergency unit is available is at least a certain number alpha. This is basically saying that for, so these three x's are, and this is I, customer, these three x's are the three locations that can serve this customer. The chances of all of them being unavailable is q to the sum of x, j, and ni. So did I invest in this location? If I did, then that counts. And then the question is, among those that I invested, what are the chances that none of those are actually available? And the answer to that question is that it's q to the sum over the eligible ones that I also invested in. And we want to make sure that this is greater than or equal. Okay, this is the probability of no emergency unit being available. So the probability of an emergency unit being available is this much, and I want this thing to be greater than or equal to alpha. That's another probabilistic constraint. If you move it around and hit both sides with the log function, you get this expression here. But then you also know that the x's have to be integer decisions, so you take the floor, sorry, come again? Ceiling, thank you, of that number. And we finally have another example of a probabilistic constraint, which is the diet problem. So this is a classic problem proposed by so here what happened is we had to work a bit to get the expression for the probabilistic constraint. It wasn't immediately available as it was in this case. And there are some situations, but it is linear, right? There are some situations where it's not even linear, but it is a convex constraint and it's workable, even though it's not linear. An example of that is the diet problem. So we have a bunch of foods. In the deterministic version of the problem, each of the foods gives us some protein, and we have to choose the foods so that we exceed a certain level of protein. But it might be the case that we buy an egg from the supermarket that's not as big as from the other village, and it has less of the protein than we expected, so we have a normal distribution describing the amount of protein in each egg. So then when we're calculating the total protein content over all of the foods that we buy, assuming that the protein contents are independent, which is quite a reasonable assumption, we get to express the total protein content as a Gaussian random variable. In this specific example, we have 6 types of food. Xi is the amount of food I we use. Mu I is the average protein in that food, and sigma I squared is the variance of food I. So if we sum up the protein over all these foods, we have a normal Gaussian with this average and this standard and this variance. So then when we're asking for the protein level, the chances of the protein level exceeding 55 grams to be lower bounded by a certain number alpha, that translates to a constraint like this. Again, what we're doing here is we are normalizing to get the standard 0, 1, Gaussian random variable. And after you do all the algebra, what you get is a constraint like this. So this mu is now a linear combination of the xi's, and the sigma is a square root of this thing here. So it's not a linear function, but it is a convex constraint, and I think I asked you in the homework of the next homework to prove that this is a convex constraint, and that means that there are it is a workable situation. Okay, and the paragraph 2.9 that follows is probably the most important content that I would like you to keep from the class. It's actually more fun than you think, Adrian. We went through it very fast. Come again? Yeah, I'm sure. But I'll give you a homework that might change your mind with specific numbers. So what we have, so probabilistic constraints are one way to avoid risky outcomes. An alternative way is to come up with measures of risk. So when we have lotteries of uncertain outcomes, we can define risk measures on them. One of these risk measures, and I should probably motivate this a bit more. So I'll remind you of this example I gave in last week's lecture. So if you remember, last week I gave you the example of a concave utility function for scoring a lottery. By scoring a lottery, I mean, how do you assign a certain level of satisfaction to some random thing that somebody offers to you? Well, a good way to do that is by giving it a score and then comparing it to the score of another random offering that someone gives to you. And one way to do that in economics is through utility functions, concave utility functions. So the way this works is that if someone offers you 100 euro, for sure, they walk up to you and they say, here's 100 euro. And you're a certain level of happy. The question is, how happy would that make you compared to if that person walked up to you and said, here is 150, a lottery where you get 150 euro with a chance of 50%, or is it 0 euro with a chance of 50%? Some of us might not care, sorry, 200. Some of us might not care because if you take the average of these two outcomes, I'm gonna, on average, get 100 euro back. So it makes me equally happy if you walk up to me and offer me the sure thing, or this, because if I get lucky, I get 200. But for most of us, it would be much preferable to walk out with a 100 euro in our hands instead of taking the chances of the lottery. So what this concave function does is it scores the lottery. It gives, and it scores it in the following way. It takes the weighted average of the possible outcomes. For the sure lottery where you get 100, you get this score over here. For the 50-50 lottery, the way you set the score is you take your utility function, you compute it at these two levels, and you assign to it the average score over these two levels. So it makes you a bit less happy, which means the way to decode this is you prefer the sure thing of €100. This is one way of scoring lotteries. So it's not the only one, and one that's very commonly used in finance is value at risk. So what the value at risk says is, and remember now the notation here in the book is Q transpose Y is referring to the second stage costs. If you remember the way we set up the two-stage stochastic linear program, we had the second stage of Q transpose Y being the costs. So what the value at risk metric says is when I'm facing a second stage cost, what is the worst thing that could happen with a probability of A%? And the way you compute that is by looking at the probability distribution function of the cost you incur in the second stage. And you find the alpha quanta of your second stage costs, and that's the value at risk for level A%. And risk managers in finance are often interested in this. So you're holding a hedge fund portfolio, and you turn around to your employee and you tell them, okay, I want the bad news. I want you to tell me the bad news. What is the worst cost that could hit our company with a probability of 98%? So for 98% of the time, I know I will be under that cost. So the answer to that is the value at risk. Okay, so that's the definition, and yes, okay, and it turns out that in the finance community, value at risk is a very popularly used metric for scoring portfolios. But there is one problem with it. It's typically in risky situations when you're pooling lotteries from different directions, the resulting portfolio is more secure because it's collecting uncertainty from more directions, and it ends up averaging out to be something more stable. This is an extremely simple argument, for example, in why insurance companies survive. When we are insuring a large number of customers, each one of them has a certain distribution of bad things that can happen to them, but if this distribution is the same and independent for each of these individuals, on average, I know with a very good accuracy how much cost is going to hit me over a large population of customers. Because if I flip the coin 100 times, I know that about 50% of the time, I know that the average will be very close to 50 of heads, for example, if I flip it 100 times. So this creates value for insurance companies because by pooling many people together, you're creating certainty about your cost distributions. And then you get to allocate it to different people depending on how bad things happen to them. But that's the source of value for insurance, is that pooling risk reduces risk, basically. Same principle in general for portfolios. When you pool different assets, you want to make sure that the risk, so this function R that I mentioned earlier, is what we will refer to as a risk measure. And here you saw an example of a certain risk measure, but you can come up with any risk measure you like. You would like this risk measure to satisfy one property, which is subadditivity. So if I pool two risky lotteries together, I want to make sure that the total risk I get is less than the sum of their individual risks. That's a desirable property for any function you decide to come up with that scores risk. It's a very reasonable property. Then one other property you would like to have is saying the following. If you hit my lottery by a certain scale lambda, so for example, if you cut back half of my payoffs from this lottery, I want the resulting score to be half of the original score I gave the lottery. Another desirable mathematical property, so homogeneity. If we hit the lottery by a constant, that just results in the constant times the risk score. Another is monotonicity. So if one lottery is first order stochastic dominated, which is a complicated way of saying if this lottery is more likely to give me less of a payoff, less of a cost, because sorry, now we're high numbers here translate to bad things happening because we're interpreting it as a cost. So if one lottery is more likely to give me a lower cost, then I want to assign to it a lower risk score. So it's a more desirable lottery. And the last property that we want to impose is if I add a constant cost to all of the lotteries, the resulting risk score is the original risk plus that cost. So adding fixed costs will just immediately translate to an added constant to the risk score. When your method of scoring lotteries satisfies these four properties, the resulting risk measure is called coherent, and it is basically a sanity check for any scoring rule you want to come up with for random outcomes. The value at risk criterion that we saw earlier it satisfies three of these, but not the subadditivity. You can have situations where you pull together uncertain assets and you get a worse score than if you held those assets individually. One example of this and this is an example that Rockefeller uses in his paper, is options. So here we have three possible outcomes. We have a certain stock that's its price is fluctuating randomly, and we define two options on the stock for two levels of payoff, which here they're not using a notation. Well, I'll give you a graphical illustration here, and hopefully it'll make things more clear than actually confusing you. So this example that I'm using here is inspired by Rockefeller's paper. So the option on the stock forces, I want to sell this option to you, and I, as the seller of the option, I'm now trying to score how risky my selling this to you is. And there are two options. One of them pays a certain amount of money to you, the person I'm selling, if the price of the stock goes above a certain level U. That's a very unlikely outcome. It's 0.8%. So stuff that's happened, the stock landing at U or above you can think of that as omega-3 materializing. If the stock is really low priced, I'm also this is option one. It's a financial instrument that I'm selling to somebody. Option two is another financial instrument that I'm selling to somebody, and it pays them a compensation if the stock price is really low. So the principle of subadditivity says that if I, the trader, sell you both of these options, then the risk that I'm taking on me should be less than the risk the sum of the risks that I would have been taking if I were selling these individually. So the liking I have for selling these together to you at the same time is better than the fear I would have if I had sold this to you individually, plus the fear I would have if I had sold this to you individually. That's the rationale here. So let's use the value at risk scoring criterion to see if that's satisfied in this specific situation. So the probability of omega 1 happening is 0.8%. The probability of omega 3 happening is 0.8%. And everything that happens in between with the price of the stock is omega 2, and that probability is it's 98.4%. So when I'm asking myself, what is the value at risk of this should be 1,000. Sorry. I'll correct that. So when I'm asking myself, what is the value at risk of selling option 1 individually? So option 1, we're going to call it psi, option 2, we're going to call it zeta. I'm asking myself, what is the worst thing that could happen to me 99% of the time? Well, if you had asked me, what is the worst thing that can happen to me 99.2% of the time, then I would tell you that in that case, it would be 1,000. But 99% of the time, the worst thing that can happen to you is 0. So for 99% of the time, you can be rest assured that you don't have to pay back anybody anything. Why? Because the price of the stock will be landing below you for 99% of the time. Likewise, if I sell this option to somebody, 99% of the time, the price of the stock will be landing above L. So the score I assign to this option is also 0. So if you sum up these scores, yes?
Why should psi of omega 3 be 1,000?
Because when the price is high, this option pays it costs me 1,000.
But then in omega 1 it wouldn't be 1,000. There are two options here.
Oh, sorry, you're absolutely right. Excuse me. Sorry. So yes, psi is the instrument that pays. Okay, so yeah, these are the other way around. So yeah, so psi is the instrument that pays 1,000 whenever prices are low, which happens at omega 1. And zeta is the other option that pays 1,000 when the prices are high. Okay, omega 1, omega 2, omega 3, and two different financial instruments defined on this space. So the var for psi is 0. The var of 99% for psi is 0. The var of 99% for zeta is 0. But when I pull these guys together, so I'm selling both of the options to someone, then I pay if the price is low or if the price is high, and I don't pay if it lands in the middle. Well, actually, this will happen 98.4% of the time. So the value at risk of 99% is actually 1,000. So the worst thing that can happen to you 99% of the time is actually paying 1,000. Now, the var of 98.4% is not 1,000, it's 0, but once you ask for the var of a higher number, it becomes 1,000. So that results in a violation of subadditivity, and it turns out I'm not really a financial engineering expert, so I can't tell you how serious this is in practice versus just being an academic exercise, but I can tell you that it does piss academics off, that it doesn't satisfy subadditivity. The bottom line of this discussion, nevertheless, so then we come up with another measure, which is conditional value at risk. And here, one thing I can tell you also from personal experience, from working for a day-ahead trading problem, is that one good thing of CVAR is that it respects subadditivity. Another good thing is you can write it in linear programming terms, and you can plug it into a financial trading model, and that works fast. It solves risk management problems fast for a company. So it's, in my experience, actually a practically useful concept, which is why I'm teaching it also in the class. I think it's something that's interesting. Now, in this effort of getting familiar with VAR, and this is the last thing I'll do before the break, I wanted to also give you a proof of why it actually satisfies the other three criteria. And this is just, warming you up to get familiar with the definition of VAR. So mathematically, what I just described verbally as being VAR is this minimization problem over here. Minimize t such that the probability of the cost being less than or equal to t exceeds a level alpha. That's VAR for level A. And the question now is, what happens if I hit my lottery with a constant, if I multiply it with a constant lambda? Will it be homogeneous? So will the VAR of lambda xi be lambda VAR of xi? And the argument says yes, it will. Why? Because when I hit xi with the constant lambda, then basically by the definition of what VAR is, we have this equality holding here. So all that changed is the argument of the probability operator. Well, all I'm going to do now here is divide both sides by lambda. Okay, so let's assume it's strictly positive. And then what we get here is that this is equal to this, and whatever the result of this optimization problem is, it's a certain number. So I can I could have as well been optimizing a scaled objective. So for example, when I'm minimizing x and the result is z, then this same number, I would get it if I were multiplying the result of this minimizing lambda x. It's the same number you're going to get as an answer, right? So it's the same trick I'm playing here. But what this number is just the VAR of xi, because I can just replace the t over lambda by, t over lambda is a variable. So it's exactly the same if I had t over lambda or some other variable t prime, and this is exactly the VAR at level alpha. So that proves homogeneity. I'm going to go to the third one, which is translation invariance, because it's a very similar argument. So VAR of something random plus a sure constant a. All I'm doing by definition is adding the sure constant here. Then I bring it to the right-hand side, so t minus a. And then I'm saying that same rationale as here. I can just add some constant to my optimization problem and add it out. Again, the number I get will be the same answer. So then I'm left with this thing plus the constant. But again, I can just substitute t minus a by another decision variable, and that leaves me with var a of xi plus the constant. That is translation invariance, and the last one is monotonicity. So what is monotonicity? As a property, it says that the probability of the first lottery being, typo, this should be greater than or equal, sorry. I will correct that too. The probability of this being less than or equal to t should be greater than or equal to that of the zeta. So that's saying that xi is more likely to be small than zeta. So to prove that variance, value at risk of psi is less than or equal to value at risk of zeta, you say, okay, suppose I solve the var of z optimization problem. So that means I'm minimizing t such that probability of zeta less than or equal to t is greater than or equal to alpha. This optimization problem will have a certain optimal solution tau zeta. There will be a certain number that solves this problem. If I take this tau zeta and plug it into the optimization problem for psi, I know, if I plug it into here, I know it must satisfy this inequality by the definition of first-order stochastic dominance. By the definition of first-order stochastic dominance, for any t, the chances of psi being less than or equal to that t are higher than the chances of zeta being less than or equal to that t. So I know that this is a feasible choice for this optimization problem. It's not necessarily the optimal choice. So the actual optimal choice of this problem, which is the var of psi, is less than or equal to the var of zeta. I know it's heavy when you first see it, but hopefully after doing a couple of exercises, it'll become better. Now, there's a very geometric, and this is the last thing I'll say before the break. There's a very like geometric way to visualize what these things mean. So, for example, the var of, let's see what positive homogeneity is saying. It says that if you take a certain lottery that's paying you off this much, and you scale this lottery by lambda, what you're effectively doing, so if lambda is smaller than 1, geometrically what's going to happen here? It's going to shrink, right? And what the positive homogeneity property is saying is that this is lambda psi. It's saying that the var of lambda psi is the var of psi moved back by a scale of lambda. That's all it's saying. So if you shrink the distribution, you move back by a scale of lambda. If you add a constant to the distribution, you're basically shifting this entire thing to the right by a constant, and the scores turn out to be what they turn out to be. And the positive homogeneity property is saying that if the CPFs of psi and zeta are like this and like this, then I like this lottery more because it's typically pays me, it makes me pay a lower cost. 10-minute break and we continue. Having said all these bad things about value at risk, let's see how conditional value at risk comes in and saves the day. So now the question the manager is asking is not anymore what's the worst thing that could happen to me 99% of the time. That's not the question, the answer. That's not the number he wants to hear back. The number he wants to hear back is, this is 99% of the time. But now, suppose I'm in this 1% of the time. What is the average of the damage we get when bad things happen to us? Another score for a lottery. What a lottery is, what any psi I give you is just a curve like this. It's a PDF or a discrete distribution, and we are just coming up with different ways of assigning scores. So the C var is the average of the damage we get, assuming that bad things happen to us, assuming that we incur very high losses. So mathematically, to define it, it's fairly straightforward. We are going to look at this distribution here, and create the conditional probability distribution function, given that we know that psi is greater than var A. How do we do that? Anyone have any ideas? Without looking at the screen. We want to take the same function, and so the mass that is left here is 1 minus alpha. So we want to say that the new distribution function that we're going to draw is going to be 0 for anything between psi up to var A. And now we're going to move all the mass into here and reshape this thing so that when we integrate over it, we get 1. So it's the same function, but rescaled so that it integrates to 1. Clear?
What does this represent?
What is this one?
Which frame variable is it?
This is psi. And
Is psi cost or benefit?
this is cost. This is cost. So high things hurt us. And we are now going to rescale this part of the remaining distribution. So what we want is a huge spike here that levels off, and the whole integral under here is 1. Okay? Well, mathematically, all I'm going to do is take the original function, shift it to the right by var A, and rescale so that it integrates, by alpha. Yes, sorry, this was alpha, because we're looking at the x-axis, now it's, yeah, because when, right, the way to interpret this is that when t is such that this thing becomes alpha, we want the new distribution to be starting its mass there, so we want it to be equal to exactly 0 at that level. So the formula is correct. And I guess an equivalent way of having written this would have been this. I want to say this is also an option for writing that, and they're both the same. Yes?
I don't understand why you need this sheet. Because, I mean, it's already at the right position, so...
So what would happen here if I didn't have the minus alpha? For t equals var alpha of psi, and remember this is the CDF we're looking at. It's the cumulative distribution function. What I'm drawing here is the PDF. Okay? Is that clear? So if t equals var alpha of psi, then the CDF should evaluate to 0. The PDF could be high, but the CDF should start counting from that point to the right. Okay? So this and this are two different ways, I guess, of writing that. Now, very important thing that for me turned out to be very useful in this project we did for the day-ahead trading of some electricity company. And to give you like a bit of context about what the situation was there, the electricity company had the generation asset. They wanted to decide if they should turn it on or not in the day ahead. And in the real time, it could have turned out, because it gets really windy in California, that the electricity prices would drop really low. But as the fuel plant was running, it was burning fuel, so they were hoping that the prices would actually be high. So they turn around and they say, okay, what should we do? And we discuss about maybe solving it with a stochastic optimization formulation. And we solved an expected value optimization problem. It's a pretty risky decision, right? You come up to them with an algorithm that tells them, if you're doing expected cost minimization, this is what you should be doing. And that does the best in terms of average profit, but there might be days, okay, this averages out to maybe $100,000 profitability per day, but there might be days where you lose $200,000 in the market. Are you willing to accept that risk? Maybe. If not, then you might want to work with a CVAR objective. So this is the way to embed the CVAR objective into your model. And this is actually exactly what we ended up doing for the project. So this theorem was proved by Rockefeller, who is one of the giants in the area and shares a Danzig Prize with Yuri Nesterov and Lawrence Wolsey from Core. Here's how you compute, well, actually, since I'm not using board anymore, here's how you compute the CVAR function. So let's take the lottery. We will solve this optimization problem, which, if you have discrete outcomes in terms of uncertainty, what is this here, the expectation operator? If you only have a discrete set of things that could happen, is this, what does this look like? Just a summation. So then what is this? It's an LP. So it's just a linear program. You define an auxiliary variable y. This auxiliary variable, whenever the costs are above a certain level t, it hurts you. It contributes to your objective function. And whenever good things happen to you, so whenever costs are low, it doesn't contribute anything, because you're not paying attention to that. You're just paying attention to the bad days. So Rockefeller proves that if you solve this optimization problem, the objective function value will be the CVAR of this lottery. On top of that, do you have any suspicion about what the t, the optimal t, might be? It's really non-trivial. It turns out that the actual optimal decision variable is the var. So you get two pieces of information just by solving a single problem. The objective function value is the CVAR, and the optimal t is the value at risk. And now you can really start massaging this and doing many nice things with it. For example, one way you want to maybe impose, the way we did it in our project was make first day-ahead decisions such that you minimize CVAR. That was our approach to dealing with risk and the problem we saw back in the project we did. Another approach might be, I want to make sure that my CVAR is bounded by a certain level T bar. Well, that's very easy to model. All you do is you write the following constraints. You know that this evaluates to CVAR. You impose this upper bound that you want on the CVAR. And the rest of the constraints are like they were before. So here the y of the notation in the book, which I should have changed, is actually a bit confusing. Here the y is just an auxiliary variable, but here the y is the second stage decisions, and the y prime is the auxiliary variable. So maybe if you replace y here with y prime, things are less confusing. So you just work again with auxiliary variables, and you count when things are bad, and you just assign 0 when things are not bad. Okay, so that's a weight control risk. And here's a couple of tricks again that will hopefully get you familiar with the CVAR optimization problem for proving the 4 properties of CRMs. So the first 2 things we prove is homogeneity and translation invariance. Like I said earlier, homogeneity means you hit the lottery with a constant lambda, you get lambda times the risk metric. So what happens when we hit the lottery with lambda? The strategy for the proof is almost the same as it was earlier for the VAR. So you get the random variable lambda xi showing up here. Now, what is this? By the way, let's look a bit at this optimization problem here. If you didn't, does everyone understand what the plus superscript is here? Exactly. What would be the optimal solution for this problem if you didn't have this plus superscript, if it were just expectation xi minus tau? Come again? I could even go further beyond that. So I want to be getting small stuff. The t is unconstrained. If you do minus infinity, this will become really large. You could go the other direction, though. So the question is, which term grows faster, the t or the 1 over 1 minus alpha times t? I believe that because alpha is something between 0 and 1, the 1 over 1 minus alpha times t moves faster. But there's a limit to this, because actually we do have the max of that at 0. So you can see the trade-off in this optimization problem. When I'm decreasing the t, good things are happening on this side and bad things are happening on this side. So, sorry, let's think of it the other way around. When I'm increasing the t, good things are happening here because this term is decreasing, and then this thing that's greater than 1 is hitting that term of the objective function. So that's helping with the optimization problem. But I hit a limit where when t becomes too big, for example, when it becomes as big as the worst case outcome of xi, I'm not getting any benefit anymore from pushing t higher. I'm only hurting by increasing this term here. So you can see that, as an optimization problem, you can kind of see the trade-off happening over there. Okay. So now looking at the properties of coherent risk measures, what happens when we hit xi with lambda xi? Well, for any number, I think we all agree that this is obvious. So then, when I have this term here, I can just scale it by 1 over lambda, and I get this, and the lambda comes outside and sits over here. So I can do that same thing with the first term, t, and I can bring the lambda constant outside the minimization, and this thing, again, with the just by replacing t over lambda by any decision variable t prime, this thing is exactly C bar, and then it's hit by a constant lambda. Clear? Now, for translation invariance, we're adding a constant r. It's showing up over here as well. So what I'm going to do is, again, change the variable from t to t minus r, and I'm going to also add a constant r, which I can bring outside the minimization. The residual thing here is exactly C var when we replace t minus r with any other decision variable. So then to prove subadditivity and monotonicity, one equivalent definition of first order stochastic dominance is that for any convex function of the lotteries, the expectation of the convex function for the first lottery that's dominated by the other is less than or equal to the expectation of the convex function of the other lottery. In our case, the convex function u is c minus t plus for some fixed t. This is, of course, a convex function of xi, because up to level t it's 0, and then it increases linearly. So this u of xi is a convex function of xi, and by the definition, equivalent definition of first order stochastic dominance, expectation of u of xi must be less than or equal to expectation of u of zeta if xi is dominated by zeta, and I'm just adding the t's left and right. When I then minimize, of course, for any t this holds, so when I'm minimizing over both sides, the inequality is preserved, and these are just the c-vars. So that proves first order stochastic dominance. Monotonicity. Okay, and for the last part, which is the subadditivity, this is clear to everyone? I'm adding two numbers, taking their max of the sum and 0. Then that thing has to be less than or equal to the max of a comma 0 plus the max of b comma 0. And I'm just applying that inequality to, so ignore the t1 and the t2 for a minute. Over here, I'm just applying that inequality to these guys. So if you add these two things up, you get this here. And we know from this property that this inequality has to hold. And then I'm just adding t1 plus t2 on each side. So then if I take expectations and optimize jointly over t1 and t2, I get exactly this result here, which is subadditivity. C-vars are coherent risk measure. You can cast them as linear programs. They're looking very promising, and we're probably going to do some exercises in the next homework on them. Okay, so one last thing about this part of the book, this subsection of the book is robust worst-case characterization of coherent risk measures and robust optimization. There's this there's a theorem that says that you come up with any scoring rule you like, and let's call it capital R. So it's a scoring rule for lotteries. It may or may not be coherent, depends what your rule is. A way to discover if it is coherent or not is the following. You give me the scoring rule, capital R, but you also give me a set of probability distributions. And if I do a worst case cost calculation over those probability distributions for a given lottery and it's equal to your scoring rule, then I know that the scoring rule is a coherent risk measure. So again, we know that the scoring rule is a coherent risk measure if you show me your rule, but you also show me a set of distribution functions, and I apply this, I'm looking for the most damaging distribution function, and it turns out that this score that I assign is equal to your scoring rule. If you can give me these two things, I am reassured that your scoring rule is a coherent risk measure. Is expectation over some probability distribution P a coherent risk measure? One way to confirm that is to go through the four properties and confirm that they are satisfied. The other way to confirm it is, here's my scoring rule. I take a lottery, and the way I assign a score for the lottery is by taking its expectation over a probability measure P. That's how I put scores, that's how I like it. And I tell you, oh, okay, interesting way to score lotteries. So, but I'm not sure you've convinced me it's a coherent risk measure. And I'll tell you, well, one thing you can do is you can take as a set of candidate probability measures this exact probability distribution and solve for this optimization problem here, which is a trivial optimization problem. The only member of the set script P is this specific probability measure. So when you're only doing maximization over one candidate, the optimal choice is the one candidate. So it's expectation over that measure for Xi. Same way, you can immediately prove without going through the whole process we went earlier that C bar A is a coherent risk measure if the only candidate in this set script P is this transformed PA. This will give you immediately the C bar. Okay. Yeah, that's correct. Yeah. Okay, so this brings us to robust optimization formulations. So now let's think of a two-stage decision-making process. So what I just discussed over here is general about scoring lotteries. It doesn't have to do necessarily with two-stage decision-making. Now, if we're looking at a two-stage decision-making problem, and let me give you a concrete example of that is, again, from work I've read, a concrete example of that is commuting units in power systems. So you have a certain group of generators and a certain group of loads, and the loads could have demands, and the demand of the loads can be anything between, it sits in a certain uncertainty set, which here will be noted as capital Xi. For example, this Xi for a single area, Belgium, could be anything between 10 gigawatts and 15 gigawatts. What robust optimization is going to do is it's going to say, go ahead, make your first decision on how to commit your units one day in advance. Do you want them on or do you want them off? Which ones do you want on? Which ones do you want off? Then, after I see what you decided with your units, I am now nature, and I'm going to roll the dice. But in fact, we're robust optimization, and usually that's how we've been thinking of stochastic programming so far. We just roll the dice and take the expectation over the outcome of the dice with demand. But what robust optimization says is, no, I'm nature, and I'm going to try and hurt you, depending on what you did. So given I see what you did, I'm going to choose the worst element out of your uncertainty set and try and hurt you in the second stage. You have the right to respond in the second stage as best you can, which is what the Q of x, xi is doing. If you remember, this is the value function for outcome xi, which is minimization over second stage decisions. And this is a robust optimization formulation. Now, if you think of this and compare it to what I just told you here, the set of probability measures is just any probability distribution function defined over this uncertainty set, and we're picking the one that's putting all the mass in the worst possible outcome for you. For me, it's more important if you just understand the spirit of the robust optimization problem, not necessarily its connection to CRMs. Okay, this is a very different philosophy from expected cost optimization, if you think about it. Protecting yourself in the first stage, knowing that whatever you do will be observed by nature and you will be hurt at your weakest possible decision, is very different from making a first stage decision and then just taking the average over things that could happen in the second stage. It's much more pessimistic in a way. It leads to much more conservative decisions. But it's another way of formulating a decision-making problem. Now, if you recall from last class, we had the two-stage yes. For the stochastic, for the two-stage stochastic linear program, we had a setup like this. So minimize first stage costs plus the average of the best you can do in the second stage. Now, what robust optimization does here, it's replacing this with this. Okay. And the constraints don't really change. We have first stage constraints and then constraints that link second stage decisions with first stage decisions through this set of constraints. And now let's assume that the only uncertain element here is the right-hand side of these linking constraints. Okay. And I'm not explicitly writing it here, but these second stage decisions are really functions of omega. So they're, you know, they're different for each different outcome of uncertainty. Now, what can we say about the dual of this optimization problem here? Does anyone remember the rules? Dual problem of this one. The easy part for me was always. Then I do remember off the top of my head that you're supposed to be hitting the right. So now remember here when we're just looking at the second stage problem, x is fixed. So the right hand side is in fact h minus wx. And our objective function was the dual multipliers times the right-hand side. And then the other thing that was easy for me to always remember is that if the multipliers are corresponding to equalities, then the dual variables are free. And what was always the pain was, you know, if it's greater than or equal, it's some inequality, but I don't remember which one it is, and it doesn't really matter if you understand the theory behind duality, which we will cover anyways. So I can tell you that the side of the inequality is pi transpose the, it's pi transpose the coefficients greater than or equal. Less than or equal, of course, yes. And then the coefficients in the objective function. So this is the dual of this problem here. So I'm just gonna plug it in. I know they're LPs, I know they have the same solutions. What I would get, and in fact, one more thing I can say about this problem is that let's write it out. Sorry, I'm sure I'm going to confuse myself at some point. So I'm maximizing over the uncertainty region, and then I'm maximizing over the pi now, which is free. Pi transpose h minus wx. subject to ax equals b, x greater than or equal to 0. The y's have been removed from the optimization and basically replaced by the dual multipliers. Okay? The xi and xi, let's assume that our uncertainty region is some bounded set, so the xi is box. Okay. So basically, all the xi and xi constraint is saying is that when I'm choosing demand, the right-hand side, I'm choosing it within this box. Okay. And since we're doing two maximizations here over xi and p, it's equivalent to doing a joint maximization over pi and xi. And the last thing I want to say about this is that maximizing f of x is equal to minus minimizing minus f of x. You buy that? You buy it. Okay. And we've arrived at this problem, a robust optimization problem. Well, no point, and this is minimization of x, no point in doing these separately. I might as well do them jointly. It's the same thing. And we arrive at a single minimization problem. What's the catch with it? And I will tell you off the. I will tell you that in general, robust optimization problems are more difficult than their stochastic programming counterparts. We know stochastic programming is a linear program. Is this an LP?
No.
That's the catch. Because
The product between pi and x.
right. And x, yes. Yes. And h. Both of them are programmatic. Yeah. So it's a bilinear optimization problem. And Bertsimas has done a lot of work on this. The debate in our area is actually very interesting these days because we've been coming up with models for stochastic programming, expected value optimization. MIT has been working on models with robust optimization, and there's this really interesting debate among which approach is preferable for dealing with power units, and because operators are actually considering bringing these models into the control room if you can make them work fast enough. So there's a really interesting debate going on in the industry, and of course the arguments you have against robust optimization is that it's very conservative. It's also hard to solve because of these bilinear terms. The arguments you have against stochastic programming is you have a humongous problem with many scenarios. It's really hard to come up with these scenarios, whereas in robust optimization, all you need to tell me is what are you afraid of, your lower and upper limits of demand. And that's very easy to specify when you have data from power system operations. So these things come up in interesting ways. Now, that's when your rectangular region is in a box. And you can also have a rectangular region which is an ellipsoid, so in 2 dimensions it would look something. Instead of having demand in area 1 and in area 2 live in this box, you could now have it live in an ellipsoid. And the mathematical expression for that is over here, and you get the optimization problem over here. But the philosophy is the same. Nature sees what you're doing and then picks an element out of this set to hurt you as much as possible. Right, and then there's all this material in the book which is purely encyclopedic about how stochastic programming relates to other literature for decision making under uncertainty. I will just give you a very brief statement. You can go through that section of the book in detail if you want, but the practical experience I have from stochastic programming is that it combines rigor, mathematical rigor, so structured problems with a lot of flexibility, and you either encounter one or the other usually in decision-making under uncertainty. For example, back before the age of computing, you had publications about how to send a satellite in space published in Russian journals, where they had a very simple description of uncertainty, where there are disturbances that will hit the satellite left and right, and the decision was what orbit should you, so how you should be injecting when you should be injecting the fuel. I don't know if you've seen Apollo 13 when they're like lost and they have to like be turning on and off the fuel, and that when you're making these decisions, there's a kinetics model that really describes in a very detailed way how the spacecraft will react, and then you could have uncertainty about radiation that's hitting your satellite and moving it left and forth. And there were models about that before computers were invented that were extremely simple and restrictive on your decision space. Your decision space would be, are you going to inject or not? And your uncertainty is something Gaussian, and you had closed form expressions, which was great. These days, by running these things on computers, you can actually build multi-stage decision-making models where if I took that old model and imposed some non-negativity constraint on some decision variable, the whole theory behind them would collapse because they were based on closed-form solutions on very restrictive assumptions, and the whole guidance policy would be a bad way to solve the problem. Whereas today, by exploiting computing, we can cast it as stochastic programming models and go beyond very restrictive assumptions. So that's the appealing thing, comparing stochastic programming to, for example, stochastic optimal control and other disciplines, or really simple versions of stochastic programming like decision analysis. So that's the gist of it. There's some more details in the book that you can look through if you're interested. And I'm just gonna spend the last 5 minutes going really fast through the first bullet here of linear programming, maybe even the duality. Either way, this part we will cover in much detail in the 4th and 5th lecture. Okay, so really quickly from this slide, one thing I want you to remember is the last inequality in the bottom. Okay, linear programming in its standard form, C transpose X, equality constraints, non-negativity, n-dimensional decisions with M constraints. What the book calls a solution is anything that satisfies a set of equalities. What the book calls a feasible solution is anything that's also non-negative. Optimal is something you can't do better than. And then we have the notion of basic solution, where we find an invertible submatrix of A, and we split the A matrix into its basic and non-basic part. A basic solution is one that solves the linear system. So when we write out the linear system, like so, what we get here is bxb plus nxn equals b. The non-basic variables go away, and if we know b is invertible, so if b inverse b is non-negative, we know that in addition to satisfying the equality constraints, it's also what the book refers to as feasible. So provided that b inverse b is non-negative, we know that it satisfies ax equals b and is also non-negative because we know all the xn's are 0. Okay? Now, when is it optimal? And you see the answer here. And the way to remember this inequality, which is extremely useful in our class, is the following. What I want to do is write out, and basically what you want to be thinking of in here is think about what the simplex algorithm is doing. The simplex algorithm is looking for ways to bring in non-basic variables to the basis. So what you want to do is write out the objective function as a function only of non-basic variables. Given a choice of basis, write the objective function just as a function of non-basic variables. Does anyone have any ideas on that? And the first hint is that you should split your cost vector into basic and non-basic parts. Given the shortage of time, I will not torment you with this quiz too much. So the annoying term is this one, because we just want to write the objective function. Once we've committed to a basis, we want to see how it behaves as a function of the non-basic variables. Here, this part of the objective function is already expressed in terms of non-basic variables. But let's see how this part of the objective function varies as we change non-basic variables. Well, we kind of have an answer to that because we have this expression here for the x's. So what we have from there, and I'm not sure if you can even see it at all, is bxb plus nxn equals b. So I'm going to write the xb as b inverse of b minus nxn. So when I'm trying to write out the objective function as a function of the non-basic variables, basically what I get is a constant term, which I don't care about. This doesn't change as the xn's change. And then I get the Cn transpose minus b inverse n xn. So as I'm playing with my xn's, this is what is happening to my objective function. If none of these, since I'm maximizing, is non-negative, that means that increasing them cannot help me in any way. There's nothing more to say about the objective function. This is what it is once I've chosen a basis. So if none of these can increase it, since I'm maximizing, I'm done. I have the optimal basis. This is the criterion for optimality, and we'll continue this next week. Okay. Did I write this? Yeah. This is right. The inequality should be, yeah. This should be non-positive, sorry, not negative, since we are maximizing. Okay. Did I confuse you in the last minute? I did confuse you in the last minute, right? Yeah, so I was wondering if this should be less than or equal to 0 or greater than or equal. We're maximizing, so if it's greater than or equal to 0, there is benefit to be gained by making an xn higher, which means positive, which means bringing it to the basis. Okay? See you next week.